There you are now. Welcome back to the garage. So today we revisit a long lost episode. So a couple of weeks ago, probably a month ago now, you came along with me as I started rebuilding this engine. This is the engine from the red Tom Pitcher 1275 GT, which is synonymous with my garage. So what we're going to do is we'll catch up where we left off. So we finished on cam timing, so we'd gotten the cam timing dialed in. The next thing we have to do is to get this camshaft buttoned up and check our end float just to make sure it's where it should be. Like I said, guys, this is an engine I'm actually rebuilding. It's not a first time. This engine came apart for no other reason than to replace that 4-bolt or to fit it with a 4-bolt center main after it broke its main cap when it was testing. So very first thing we have to do is we want to get this cam tapped into place. So where it was before we had it set for doing timing, you can just, I always leave it really free on here so I can just pop it off and pop it on for checking timing, but obviously now it needs to be locked into place. So that's the lock-in washer that we use. It's been used a few times, but there's no problem reusing these. I generally try and go to a new spot on the washer each time, because as you keep bending these washers up, it introduces a weakness. So you can see the engine's been apart twice. There was the first time, there's the second time. So now more than likely we'll go over here for the third time. Once you sort of get all the way around the washer, you really want to dispose of it and replace it with a new washer then at that stage, because otherwise, you know, I don't like to bend up a lock tab more than once. As I said, it introduces a stress fracture in it and it can fail then while the cam is in operation. Now, how we torque this camshaft, I do something unusual on my camshafts, which other people may or may not do, but I'm going to show you how I do it. And this comes from years and years of experience building engines. So the torque on this from factory is really high. The torque on this from factory is something close to 80 Newton meters. I think it is 80 Newton meters actually, is the OE torque on this. So what we want to do is just, first of all, just get the cam locked. What I'm going to pull it to here is I'm going to pull it to 60 Newton meters and then I'm going to turn it 90 degrees. What do I mean by turn it 90 degrees? I'm going to show you now in 1 second. So let's just pull our torque first of all. So that's our torque at 60. Now, why I turn it 90 degrees is because it gets rid of the problem of friction. Okay, so torque with a torque wrench is very specific, or is very specifically affected by friction. Now you can grease this nut, you can grease these treads, but it's got a real big surface area and it's on a real soft washer here because this is a locking washer. So getting really accurate torque numbers is very difficult. So what we do is we pull it up to a low torque number, which in this case 60 Newton meters is really quite a low torque number. That's a known setting. What I've done over the years is I've developed this technique, and I know that at 60 Newton meters, if I turn this nut a further 90 degrees, I'm at the actual torque specification for this nut and tread combination. It's something that I've been doing for a long time. Not everybody will agree with it, but I've built enough engines and I've never had a camshaft nut let go or fail that I'm completely confident on how to do it. So when we do this turn through 90 degrees, you can buy an angle protractor which goes onto your socket and you can lock it up and turn it through 90 degrees. But basically what I do is I mark my start point, which in this case is the center of this flat, and I mark where my finish point is. I mean, 90 degrees, guys, it's pretty easy, right? You know, through there is 180 and across there is 90. Yeah. A degree or two here is not going to make a difference. If you're out by a degree or two here, it won't make any massive difference. So bring your nut on then to the 90 degrees and that will get you at your torque specification. Yeah. And that has it there. So by turning it that further 90, you're getting rid of any amounts of friction. Friction is not an issue here. You're bringing it to a known specification. that's the way I do it. Some people have their own way of doing a lot of different things. Am I suggesting this is the way you should do it? Nope, I'm just showing you that that's the way I do it. Next thing I want to do is to bend up this lock tab, but before I do that, I want to check the end float in the cam just to make sure that I have the correct end float. I did have it before, the camshaft hasn't changed, the back plate hasn't changed, or the washer hasn't changed, but this is a full out race engine and you got to check that stuff as you go along. I now need to find my dial gauge. So now I have the dial gauge set up here on the end of the camshaft, and with my screwdriver I'm just going to check the end float in the camshaft and it'll be read by the dial gauge. So we have 0.1. Let's check our zero again. Okay, 0.11. Okay, that's perfect. That's exactly what I'm looking for. Generally speaking, the end float that people would go for on this, I think the book recommended figure is actually around 0.1. It's somewhere very close to that. For a race engine, I will accept anything between 0.08 of a millimeter to 0.15 of a millimeter. All right, so anywhere in that sort of ballpark for a race engine is more than fine. You don't want to have any more end float than that because what will happen is you don't have much play in the timing chain before you'll start to get a camshaft that runs out of sync with the timing chain. You want that camshaft running dead in line with the timing chain. If it goes one way or the other, if you get too much end float, also what can happen if you've got too much end float is that the cam follower can run slightly off the lobe. So the follower sits on top of the lobe essentially, and the cam lobe lifts the follower up, which opens your valve. If you get too much end float, what can happen is the cam can migrate off the end of the follower. And if it migrates off the end of the follower, as it lifts it, you're going to get a huge wearing angle happening there. So anywhere between sort of 0.08, 0.15. It is more than good enough for this, but I'd try and get it to the lower side. 0.1 is spot on for a race engine. It allows a little bit of room for everything to warm up and not get tight, but not enough that it'll cause any problems with either the cam chain or where the follower sits. So we'll bend up this lock tab, and then once we have that lock tab bend up, we can get the timing cover on and get that fitted into place. So I always start these with water pump pliers because it just helps you to lift it up away from the cam gear and just stops it from doing the cam gear any kind of major damage. I see people going in here with screwdrivers and stuff, and you start nicking and cutting the cam gear. You get in there afterwards with a punch like this, and you can flatten out the square it out. Now, you'll see something that this is a little trick of the trade I always do as well, which is just to bring the ear in just slightly there. So just that little knock the ear in that side. So what that does is it just stops. Sometimes what can happen is if this was to work its way loose and this had to come into action, sometimes what can happen if you don't have that ear in there is the actual friction or the power of the nut against the lock tab will move it over. If you bring the ear of the lock tab in just like that on either corner, what happens then is that it actually catches the nut as well. So it has to escape that catch and then bend the ear over. So it just is that extra little bit of security along the way to give yourself a bit of extra precaution. Okay, a very important part that I don't know how many engines I've stripped over the years and found missing. This is a throw out ring. Okay, and it sits down here on top of the crankshaft sprocket that's driving the cam. The throw-out ring is designed that when oil comes out of this chain under high pressure, it hits that throw-out ring and is driven back down against the plate. If you leave this oil throw-out ring, you have nothing to stop the oil coming out and trying to hit the seal in the timing cover. The other thing as well is this is also a washer that people don't realize. This is a washer to spread the load across the top of the sprocket from the drive shaft pulley. So when the drive shaft pulley is in place, it comes down and it hits that throwout ring, and it's a washer, so it helps spread the load. Otherwise, the sprocket is sitting on all the indentations and the high spots of that sprocket. So the pulley would be sitting against that. Whereas when the throwout ring is in place, it acts as a washer, just to give that throwout ring something that is slightly softer metal to sink into and get that torque to sit strong. So once you have that in place, the next thing is a gasket. Now, there's about 3 million schools of thought on this gasket as to whether we should put gasket sealant on here, not put gasket sealant on, put sealant and no gasket. I just use good quality paper gasket on here and torque the bolts to the right specification. I don't use any gasket sealant or any gasket goo. My race engines come apart every sort of 15 or 20 hours anyway, so they don't do huge periods of time between being changed. If you put gasket goo on there, when you're going to take it apart, it can be a right pain to clean it off and stuff. If I was building an engine for a customer for a car, I would put gasket cement on there. I would use something like Durco. This is my favorite gasket cement out of all of the ones that's out there. It's made by L-Ring, and it's a really nice neutral gasket cement that seals very well and is reasonably easy afterwards to take it back off again and, you know, prep up the surfaces. But for a race engine, I don't use it. I just use a good quality gasket. That's the gasket we're going to put on there. So these are a set of studs that I put in. This is a modification I do, and I'm going to get Billy to show you another angle of that. So basically, what are they? They are a countersunk cap head M6 bolt. I countersink the other side of the plate, put the bolt in and tack it in 2 places with the TIG welder. And that just means then that I have a stud up here that's a really good fastener. It's not going to move around the place. It's not going to give me any problems. Okay, next thing to do is to put the timing cover in place. Now this has a new seal in it, so I'm not worried about the seal needing to be changed. Obviously, if you're building your engine, make sure that you put a fresh seal in. This one would have had a seal just not long ago, and it's still lovely and soft. There's no sign of it needing to be changed. So put our cover in place, and then this is the trick, guys. You get your pulley and you put your pulley into place as well. What is this doing? This is centralizing the cover. So this makes sure that the seal and the cover sits in the right spot. Just get that pulley sitting down in place. And now what we know is there's a good bit of play in all these bolt holes. So that means that now the cover is sitting centrally with the seal. If you don't put that pulley in place, you just put this cover on and bolt it down where it lies, it can be as much as a couple of millimeters off one way or the other. When you put your pulley in, it puts pressure on one side of the seal and leaves the other side of the seal slack, which what that will result in is the seal will wear very quickly and start to leak. If it leaks, obviously, then you have oil everywhere, and unfortunately, where it might leak from is not a good spot for trying to get at, because it's in behind the radiator, it's in behind the fan, and it's down deep in the engine. So getting this right early doors saves you a lot of grief. Okay, people ask me this as well: which order do you put these bolts in? First thing I'll show you, these are lovely heavy washers that I make myself for this. I just buy one of these heavy M6 washers and I grind the corners off them. So grind 2 flats on either side, and what that does is it fits in there just really nice and neat, and helps hold that cover down really well and stop it from moving around. So these are the bolts that you should fit first. Now depends on what flywheel setup, or sorry, what timing chain setup you have. This is an A engine because it's from the 1275 GT, so it has no timing chain tensioner. The timing chain that I use in here, it's a full race timing chain with full race gears. It doesn't need a tensioner. Your setup might have a tensioner, and it'll have a set of bolts coming out this side with a tensioner. If you're using a flywheel setup with a tensioner, then it looks slightly different to this, but it's the same thing. Okay, you just have these 3 extra bolts out here. When you're putting this down, the big bolts are what goes in first, okay? So you've got some 7/16 and you've got some quarter. These are the quarters, or in this case I've changed them to metric. But you've got some 7/16 and you've got some quarter UNFs. So what I always recommend is you put your 7/16 in first, because they're holding the cover down and the back plate, and then the quarters in afterwards because they are only holding the cover to the plate. Don't forget about the ones over here. They're also holding down that cover, so they need to be there. What you'll notice, guys, is that these are different fasteners to what you'll have probably on your engine. On your engine, you'll have nuts and bolts. Well, you'll have hex head fasteners. These are A2 aircraft quality stainless steel fasteners. It's something that I use on all my race engines for two reasons. One, that aircraft quality A2 is just a superior bolt, and obviously then you're not dealing with the problems of corrosion and stuff like that on a bolt that you need to be taken in and out regularly. Okay, next job after this is the oil pump, so we'll get that into place next. I'm going to take the oil pump apart. This is the oil pump from the engine, and it has been used. This is one of the turbo type AP oil pumps. I'm going to take it apart and measure it. There's no need to replace this oil pump if it's in good condition. So we start by looking to see have we any major signs of wear. So far everything looks pretty good there. I think I might lap the surface of that a little bit on the sandstone because there is some little signs of friction on it. Now, how we measure one of these oil pumps. So the clearance you're allowed on an oil pump is no more than 5/1000 between the tip of the rotor and the annular outer gear, okay? So no more than 5/1000 or 0.127 of a millimeter. So I'm going to start off with a 0.5, which is 2.5 feeler blade. And what I'm doing is I'm putting the feeler blade between the tip of the rotor and the outer annular gear. So in the case of that one, I can't actually get that feeler blade in there. That tells us that, well, just maybe I can just work it in there. Yeah, so I'm just getting that feeler blade in there. Let's come up to the next one and try that. That's not going to go in there, so that's good. Let's try our next one there. Okay, so we're getting our feeler blade in on that one. Let's try our next one. Same again, we're getting our feeler blade. So that's it, we've gone around now. We'll go one more time actually, because you've got 1, 2, 3, 4, 5 and 1, 2, 3, 4. So it's epicyclical. Epicyclic. It's epicyclical. Goes out on an epicycle every Sunday. Okay, so, and it's important that you're right at that tip, right at that crossover point. So, can't get in that one. So I just want to get the bigger blade now, which is 0.1, and just make sure on those ones that we did get the 0.05 in, that we can't get the 0.1 in. So it's just a case of the same thing, bringing your two around. That won't go into that one. There's our start point. Can't get it into that one. Our next one. Can't get it into that one. Our next one. Just barely get it into that one. Next one. Can't get it into that one. And our last one. Same thing, just barely at that leading edge, but won't go in any further than that. Okay, so that tells us that our pump is serviceable. It's still within the measurements. It has clearance, but it hasn't gone over clearance. If it was measuring up and you could get that 0.1 or the 0.125 blade in, or the 5/1000 blade in, then it's probably time to change the pump up. Believe it or not, a thousandths clearance in here can be as much as 5 pounds pressure when the oil is hot. So that's a big drop in pressure for about what might seem like a tiny amount of clearance here. These have to run with a really tight clearance. I'll very quickly show you how I lap in the components, and then we'll get to putting the pump together. So what I'm going to do is I'm just going to lap this back plate a little bit, because I don't like the finish on the back of it. I start by just giving it a little rub on the oil stone, and that's going to just take out any of the high or bad imperfections that might be on it. And then we'll move over to some sandpaper then. Okay, so that's just taking out those couple of imperfections that were on it. Now what I have here is a sheet of glass. Anybody familiar will recognize this as a piece of glass out of a Mark 1 Mini side window. And I've just stuck some super glue to it. This is the, be broken sheet of glass now from the Mark 1 Mini. So I've just stuck a piece of sandpaper to it, and I just have some light cutting fluid on here. So all we're doing is we're just using this to lap the surface in. We're not actually taking any metal off here. We're just simply bringing that surface, taking any of those little high spots that were in that plate out. What sandpaper is this? This is 2000 wet and dry sandpaper. Is what this is. 2000 wet and dry. Change your direction. Don't go in the same direction any one time. Move it around, and you'll bring that surface into lap. You can do this on a granite surface plate. You could do it on a known good piece of flat cast iron, like the side of an engine block, something like that. But glass always works really well for me, and I always get really good results from it. Glass is pretty flat, you know. The clearance levels that are on an oil pump like this, it's perfectly fine. Yeah, it's a ground. These oil pump covers are ground anyway, so you're really just taking the high spots off. You'll know when you're getting close, because you'll feel this sucking down to the sandpaper, and it'll take more and more effort to actually get it to lap, to get it to move. All we're doing here is we're cutting down on the chances of this plate leaking. Some people ask, why don't I put some maybe gasket cement or something on it? But the clearances are so tight here, there is actually no room for gasket cement. It wouldn't work. Okay, so now you'll see how the surface is starting coming into lap. See that grey area that's starting to come up nice and bright and grey there. You can see the quality of the way these pumps are ground is very poor. You know, 20 years ago when you got one of these, if you rubbed it on this sandpaper, the whole thing would come up shining. Nowadays it seems to be completely acceptable to send pumps out with surfaces like this. It's unfortunate, but it's the way it is. We'll keep going lapping this until we get the whole surface of that bright and grey, and then the pump will be ready to go back together. So just before I put this pump back together, I just want to show you how I test it. So just on a plainer piece of glass here, I've used some micrometers bluing agent, which I've put down here on the glass. And basically what the bluing agent does is it makes a film across the glass that you can put a surface you want to test flatness on. And if there is any spot that isn't flat or isn't at the right height, it'll show up as either not blue or as a lighter shade of blue. So what we can see now on this oil pump back here is that the blue is even all the way around the mating surface, so where the pump is going to need to seal. I'm also going to show you a quick trick that we have used, or that gives you an indication of how good your pump seal is, or whether you've got an oil tight seal or not. If you just clean off that engineer's blue and put just a little bit of engine oil on the surface, just rub it around with your finger, and then use one of the bearing surfaces from the pump and put it down. If you've got a good flat surface with a good seal or a good connection, you'll have a oil film will build up, and it'll actually physically hold the two parts together. So it gives you kind of an idea, and it'll take a bit of force to pull them apart, and that'll show you that you have a good sealing surface. So when these pump elements run together now, they will actually seal properly. Would that pump have run and worked? Yeah, it would. Would have worked fine, because oil has a viscosity to it and it will seal. But the pump inside the engine would always be leaking an amount. By lapping the surface of the pump like this, we reduce the amount of oil leakage we get at the pump. Well, is that to get more oil pressure in the engine? Not necessarily, but it's to reduce waste and loss. Every time you leak oil out of the system, it's oil you've had to pump. Oil you've had to pump saps power from the engine. If it saps power from the engine, that's less power that is going through the drivetrain to drive the wheels. And it increases by the square. So by the square of loss, it increases. So what might seem like minuscule losses there add up over and over and over to become much bigger losses. We're going to clean the pump thoroughly now with some engine degreasing. We're going to get some fresh lint cloth, wipe all the pump surfaces down, lightly oil them, put the pump back together, and then we'll fit it to the engine. When I'm fitting oil pumps, I like to use the best quality gaskets I can get my hands on. These are the sort of really high quality gasket from Mini Spares, which are two different materials, one suiting aluminium and one suiting the cast iron. They're really a nice gasket. They last well, and they're worth the small few quid more than they cost. Well, small few quid more than the sort of cheaper option of them. I've pre-filled the pump with a little bit of engine assembly lubricant because I have it on hand, and it just gives the pump a seal to draw oil up. Because this is a race motor, I'll be pre-lubing it anyway, and I'll show you the pre-lubing process where we put hydraulic pressure through the engine to bring it up. But it's always a good idea to pre-lube your pump anyway, because it'll make sure that it'll take up oil pressure straight away and it'll bring it up. The next thing we have to do is to get this pump into place. It's very important that this gasket is orientated the right way, okay? So there's a bigger hole and a smaller hole in it, and then the holes for the bolted surface or the bolting down surface. You'll see in this block there's actually 4 bolting holes in the block, because I've modified this block to take the later type oil pump, which has its the mounting bolts across it, whereas the older block had it in a sort of a 3-way configuration. So just line up the pump drive slot with the slot in the camshaft, drop your pump down on, and line it up then with the holes. Just always take a look down through the hole to make sure that your gasket hasn't moved. You'll know if this seal lines up with this drain hole here on the bottom of the pump anyway. I use, again, as I said, very high quality fasteners, A2 aircraft grade stainless steel fasteners. You'll probably have a hex head fastener on the pumps that you have. Do I recommend these? I've been using them for a long time on my race engine builds with very little problems. So I can recommend that these are really good if you buy the high quality ones. Unfortunately, like anything that's high quality, it isn't cheap. They're an expensive fastener, so don't expect to get them for kind of small money. Once we get these kind of run down, then we're going to torque them up. It's very important that you don't skip the step of torquing the oil pump bolts, okay? Because the gasket is very sensitive on the oil pump. If you over torque the oil pump bolts, it's not that you're worried about pulling the bolt. You could over tighten the bolt and stretch it, but it's actually that you'll affect the gasket and you'll cause it. There's only very small passageways of gasket on the oil pump, and if you over torque it, the oil pump will, when the engine gets hot, will sit down and it'll push the gasket out and you'll lose sealing. I've come across a few engines that were built by people who were a bit have a go in the whole situation and probably didn't torque the oil pump. They probably just tightened it up, and you know the old story, when you're not torquing something tighter is better for a lot of people, because they're worrying about whether they've tightened it or haven't tightened it enough. And the problem the engine had was twofold. One, it had low oil pressure all the time, and the second thing was it would take the oil light a long time to go out when you'd start the engine. And the real reason why that's the case is simple, because the pump was drawing air. It was cavitating the oil, and it can't get oil pressure up quickly. Then you've got aerated oil. And it was really clear when you looked on the end of the dipstick, the oil was white. People often think white oil is because water's in it. And that can be the case, because water will emulsify into the oil and you get this whiteness. But also aeration in the oil will show as a whiteness in the oil, because the air is getting emulsified into the oil in the same way. There's a right way and a wrong way to torque a bolt, and here's a really good place to show you when we're pulling such a light torque. So the torque on these is 11 newton meters, which is really, really low. What is that? 9 foot-pounds, is it? No, it's actually, it'll be probably in foot-pound inches, or pound inches, should I say. Yeah, it is in pound inches. It's 100 pound inches, or 11 newton meters. So how you torque a bolt is you must arrive at the torque in one motion. So you pull the torque wrench and you're looking for the torque wrench to go. So that's the torque wrench going. Sometimes people don't get it on the first pull. I'm going to demonstrate to you what that would be like. So where I turn the bolt and go, all right, now I just need to reorientate this and then I'll get the torque. That's no good. You can't creep up on the torque like that. You must get the torque in one smooth movement so that you break inertia. I'll show you what I mean by breaking inertia. If you've ever tried to push a car that was stopped and you were helping somebody with a bump start or something, and it takes a lot of effort to initially get the car to move, but then as soon as the car is moving, you can kind of push it along easily then without as much effort. That's breaking inertia, that's getting the thing moving. Bolts are exactly like that. There's friction between the threads of the bolt and the bolt hole. There's friction between the bottom of the bolt head and the mating surface you're using the bolt to clamp down. If you, when you pull on that torque wrench the first time, you're breaking inertia. You're getting that bolt moving, and then you're waiting for the torque wrench to register the actual tightness of the bolt. If you creep up on a torque, inertia can fool you into thinking the bolt is actually at that tightness. It's already tight, but actually what you're actually just feeling is resistance in the tread and not coming up to torque. So I'll show you just one more time. So I'm moving the bolt and I'm coming up to torque in one movement. Something like this where it's very low torque, it's critical that you do it in that situation. Higher torques like 80 or 90 newton meters or 60 or 70 foot-pounds, it's still critical, it's always critical, but it will have less of an effect the higher the torque goes, because the breaking of inertia is easier. Okay, next thing to do now is to get the top of the block ready for the cylinder head to go on, now that we have our oil pump in place. I have the head studs installed now, and I just want to point out one or two things before I stick on the cylinder head. So there's a couple of things that you have to watch out for when you're getting a block prepared for cylinder head to go on it. Putting in the studs is important, that you get full depth of engagement on the stud. So you don't want to see any of the threaded portion of the stud sticking out of the top of the block, basically. So that's screwing into the block, and the last thing you want to see is some of that thread portion of the stud above the block face, because that means you're not getting full thread engagement. If you've skimmed the top of the block a few times, or the machine shop has skimmed the top of the block to bring your compressions up to the right height, then the holes that are put in by the factory may not be at the correct depth. The best solution to this is to do this before you build the motor. I built this motor a few times, so I know these are at the right height. And just before, if you remember back to our very first video on this, we had skimmed the deck of this block because we were getting a bit of leakage across cylinder 2 and 3. When I had this in the milling machine, I checked my bore depths to make sure that the stud would go all the way in on all of the bores. One or two of them I had to drill them slightly deeper and tread them slightly deeper. One of the ways I've often got away with this is by getting a plug tap and running the thread all the way to the base of the hole. Oftentimes the bore in the block is actually deep enough, it just hasn't been threaded all the way. In the factory they used a semi-taper threading die when they threaded these all 9 at once, and they had a semi-taper onto them. So what that means is the thread at the bottom has a little bit of a taper to it. If you get a plug tap and run it, you'll complete the thread all the way to the bottom of the bores in the threaded portions, and your stud will go all the way to the bottom. You may get to a stage where you still don't get full thread engagement. I've seen a few people hacksaw the end off the stud. For God's sake, don't do that. You're losing holding ability of the stud. The stud requires all of that tread to be held in the block to give it full holding ability in the cast iron. So the only way of repairing it, if your tread is sticking above the block, is to make the treaded hole deeper in the block. That is the repair. Okay, when you're putting your head gasket on, this happens quite often when you see people putting head gaskets on. They don't know which way to put the head gasket up. So this is the BK450, which is still a really good gasket from Payne. And there is an up and a down side to the gasket, and I'm going to show you very quickly how to know what that is. If I show you on this gasket, you can see that the firing ring is completely smooth here across the bottom. And if I flip the gasket up the other way, you'll see there is transitions on each one. Okay, you can see that transition on each one. That is how you know that is the top. Those where the firing ring is pinned over and has that sort of transition there, that is always the top of the gasket. So I've come across a good few engines with this gasket on this way around. Now, the manufacturers of the gasket do allow, they put an oil hole on both ends. So the gasket can work this way, but it's wrong. The way the gasket should be is this way up, with those transitions at the top. Another thing you're going to find when you put a gasket on an engine is you'll find this, it's just not dropping down on the studs. And the reason why it's not doing that is because the stud is quite long coming up out of the block, and the tolerances for drilling, boring and tapping these in the factory originally were quite loose, shall we say. So what happens is that the stud itself, they move a little bit as they're going up. Now, it's not a problem when the cast iron cylinder head comes on, it'll square up all those studs and straighten them out, but for putting your gasket on, you've got to be a little bit careful. Some people would recommend putting the gasket on the block and then winding the studs in through the gasket. I'm not a big fan of that because it can hide the way your tread in engagement depth. So I much prefer when I'm doing it just give the studs a little bit of a move like that. You can pull one against the other just to get it to sit down, and it should go down like that, nice and handy. You're not looking for the gasket, you don't want to force the gasket down basically. So you're just pulling studs together like that just to get them to allow that gasket to sit down and get down on the block into a proper place. Before you put your cylinder head on, it's a really good idea to take a look down at your gasket and make sure that it is sitting in the right spot on the block. Okay, I offset bore these blocks to my own measurements, so I know that these blocks or these gaskets are essential as they can be for the bores, but in a lot of engines that's not always the case. What I recommend is that if the gasket doesn't sit central and it looks like it needs to move a little bit one way or the other or in any particular direction, you can take the gasket back off and alleviate the hole around the stud to allow the gasket move into the right spot. If you do that, you just have to be careful when you're putting the cylinder head down onto it that the gasket is in the right spot when the head comes down. If it's not, what can happen is it can move off course. The piston then, when it comes up to the top of the block, can hit the firing ring of the gasket. If it hits the firing ring of the gasket, it normally weakens it or creates a sharp edge. That sharp edge will get hotter than any other part of the gasket and it will eventually fail there. So it's something that it's important to make sure that you get that gasket in the best position possible. Last thing to do then is to put your cylinder head on. You want to make sure that the surface of the cylinder head is completely flat and clean. Now, this cylinder head has been actually diamond ground for me or diamond machined for me, so I know it's absolutely dead level and dead flat. I don't go at it with sandpaper or Scotch-Brite or anything like that because this surface is actually so well machined flat that rubbing it with Scotch-Brite or sandpaper will put scratches and grooves in it that shouldn't be there. So the only thing I'll ever do is use a bit of the magic spray just to clean off any grease or oils, and as long as the cylinder head is nice and smooth and flat, that's it. I just put it on like that and I won't go around potentially damaging the surface. The only other thing I'll point out to you is that I block up one or two of the waterways in the cylinder head. So I block that one up there, I block that one up, and I block that one up. Don't worry, that's not going to stop water circulating this end of the cylinder head, but what it will do is it'll drive water down the cylinder head to cool this end of it better. It was something that's been done for a few years now and is very successful in getting the cylinder head temperature to level out if you can't use the likes of a dry deck. If anyone is looking for a good video on dry decking a mini cylinder head, Turbo Phil over on turbominis.com has a really good video about dry decking cylinder heads and the different pros and cons to it and the different ways you can go about it. So well worth taking a spin over to Phil and having a look at that. Just getting this cylinder head down now into place. Remember what I said to you earlier on about the fact that those studs have to kind of straighten up, and that's what it is. Engines require finesse, lots of taking your time and getting them to work without, don't hit them with hammers, or don't try and bang stuff into place or get them there. Okay, so the cylinder head is now sitting down where it should be. And one of the things I always do with cylinder heads before I torque them down is I pull them forward onto the studs so that it's lying flat against the studs. If I do this, you'll see that movement that's in the cylinder head. That's the way the cylinder heads are machined. What you want it to be is forward tight against the studs and flat. So you want to feel all 4 of those studs at the back holding the cylinder head, and that is the best lined up it'll be for the combustion chamber. Do that just before you torque the cylinder head down. Okay, I think we're going to end this video here, and I'm going to do a final video of me fitting the rocker gear, the gearbox, and the timing cover, or sorry, the drop gear housings, and then the clutch on. And then that'll have this engine ready to be put into the race car, and then we can get it connected up, get oil and water in it, get oil pressure up, and get this engine started. Thanks very much for joining me on the video. I hope you're enjoying these engine build series videos and you're getting a bit out of it. If you are, give us a like and a comment down below on anything that you want me to elaborate on more, or any other information, or just generally to have a chat with us on the channel. I love reading all of your comments. If you're new to the channel, you are very welcome. Thank you very much for coming along and watching our video. If you think we've earned it, give us a subscribe and watch out for more of our content. Other than that, I'd see you guys on the next one.